Hi everyone, in this video I'm going to talk about how to do the steady state approximation, which is how to write a rate law with a slow second step. So when the second step is slow, we can't just write the rate law for the reaction mechanism based off the stoichiometry for the slow step, like we would when the slow step is first. Why? Let's look at it. If I said this reaction first, when you combine them, the overall reaction is going to be, well, NO(Br2) is an intermediate, so that will cancel out. It's going to be 2NO plus Br2 makes 2NO(Br). And if I said, what's the rate law for this reaction, you would write, if you wrote the slow steps, you would write this. This is a problem though, because NO(Br2) is an intermediate. I cannot control the concentration of an intermediate because it's not a reactant. Rate laws should only have reactants in them. And it's an intermediate. Intermediates are often, they're unstable. We can't control their concentration. They just cannot be included in a rate law. And so instead, we have to do what's known as the steady state approximation. And so these steps explain how to do this. So first, it's not in the notes, but this step is fast. And you probably don't know this yet, but we have a forward arrow or reverse arrow, which means this reaction goes in reverse. Oftentimes, these problems will say fast, and they will say equilibrium. If they don't say equilibrium, equilibrium can be implied if you're asked to find a rate law for a fast step. Because at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. And so for number one, I'm going to write the rate law for the fast reaction. It would be rate equals K1. I'm going to call it K1 because for the forward reaction, it would be NO times Br2. But this reaction is at equilibrium, which means forward equals reverse rate. And I'm going to set that equal to the reverse reaction's rate, NO Br2. Okay. That's what you do first. Again, you write the rate law for the fast reaction, setting the forward equal to the reverse. 2, we can identify intermediates, which we already did. NO(Br2) is our intermediate, and rearrange the rate law so intermediates are isolated. So to isolate NO(Br2), I would divide both sides by K to the negative 1. Now, and these K's are going to cancel out, and so we're left with rate equals NO times Br2. That would equal NO(Br2). Again, those divided out, those divided out. So I have what my intermediate equals now, which are those two. Step 3, write the rate law for the slow reaction. I'm going to write the rate law for the slow reaction. Rate equals K2 times NO(Br2) times NO. Now, again, as we said earlier, you cannot have an intermediate in a rate law. But I know now from step 2 what NO(Br2) equals. So instead of writing NO(Br2) right here, I'm going to write what it equals up above. So we substitute in what the intermediate is equal to. And we're left with rate equals K2. And instead of writing NO(Br2), I'm going to write what it equals again, which is the concentration of NO times the concentration of Br2. That's that, times the concentration of NO. And that would be my rate law. You could also write it a little bit neater, and instead of having NO twice, we could say rate equals KNO squared times Br2. Both are acceptable. Now let's look at one that's a little bit more complicated. Ozone's rate law. and we're going to follow the same steps again. So step 1, write the rate law for the fast reaction. It doesn't say it right here, but I'm telling you it. This one is the fast step. This one is the slow step, and that fast step is in equilibrium. So again, I'm going to set the rate of the forward equal to the rate of the reverse. So K1 times O3 equals K negative 1 times O2 times O. Again, setting this forward equal to that reverse. 2 said identify intermediates. When I look at this reaction, O is an intermediate because it's a product, then a reactant. O2 is not an intermediate. And so I want to rearrange the rate law so intermediates are isolated. I want to isolate O, not O2. So I would divide both sides by that. Okay, those cancel out, the K's cancel out, and I have the concentration of O3 divided by the concentration of O2 equals the concentration of O. 3, write the rate law for the slow reaction. Slow is second, so rate equals K2 times O times O3. Step 4, substitute in the intermediate equation. So substitute this in where the intermediate goes. So instead of writing O, I'm going to write what O equals. So rate equals K2. I don't put O, I write what it equals. O3 over O2 times, and pull that down, O3. Now this is pretty messy. I don't like this, so what I'm going to do is rewrite it. There are 2 O3s, so I'm going to square them. O3 squared. And I don't like anything at the bottom of a fraction. I don't like fractions. So instead of having it at the bottom, I'm going to pull it up and say it's to the -1. Now that is definitely unusual. But it is most definitely a thing, and that would be the rate law for the decomposition of ozone. So this is it for steady state approximation. It's really, if you follow these steps, pretty simple. Set the forward in reverse of the fast equal, isolate your intermediate, write your slow step where the intermediate is, substitute in what it's equal to, and simplify your rate law until it's prettier. I hope this helps.